Okay, so let's do a related rates problem. Let's say a bird flies horizontally in a straight line and passes over your head at a height of 50 feet. T seconds later, the angle of elevation, theta, is pi over 4. Just to be clear, if this is you, and this is the bird, and this is the ground, the angle of elevation is this angle. That's just some terminology. The angle of elevation is like, what angle do you have to look up in order to see the thing that you're talking about the angle of elevation of? The angle of elevation of the bird with respect to you, it's just the angle that you have to look up away from the ground in order to see the bird. So that's this in this picture. And so in this particular instant, the angle of elevation is pi over 4, but of course the bird is moving this way. So the angle of elevation is actually decreasing, as you can imagine. If the bird is moving this way, then this angle would decrease because you have to look this way to see the bird. And we say that the angle is decreasing at 1/10 of a radian per second. And the question is, what is the speed of the bird? Okay. So I started drawing a picture already. Let me put some more information on the picture. Like, for example, the height of the bird is always 50 feet. And let me point something out. When I'm putting labels on various quantities in the picture, there are really two types of quantities. There's ones that are constant and then ones that change throughout time. And this can be confusing because we are typically talking about a particular instant when we're doing related rates. And at that instant, you have numerical values for all of the variables, even the ones that change over time. But it's important to acknowledge which ones are changing and which ones are always the same. This number is always the same. The bird is flying horizontally, and so this height is never changing. The bird isn't going up or down. This is always 50 feet. If I'm talking about a quantity that never changes, then I'm comfortable just putting that number there. But if it's a quantity that does change, like the angle of elevation, I'm not going to put in the particular number that it is in the instant in question. I'm going to label it as a variable. Even though I know that in the instant in question, theta is pi over 4, I didn't just write pi over 4 here. I wrote theta because I want this picture to represent like a general instant, not just the instant in question. So, of course, in the end, we're going to have to fill in values that are valid at the instant in question. But first, we have to do some calculus, and we have to do some derivatives. And for the sake of that, it's very important to know what's changing and what's not. Anyway, the question is about the speed of the bird. And the bird is sort of going this way. I mean, I guess I can draw, this would make it a rectangle here. So the speed of the bird, since the bird is just flying this way, maybe it makes sense to label this distance as like an x, and then the speed of the bird is just the rate of change of x. Like x is the distance from here to the bird, And so how fast the bird is going would just be the rate of change of x. Of course, this x is the same as, like, that would make the bottom of the rectangle also x. So actually, maybe I'll focus on this bottom triangle. Okay, what I need is I need to set up an equation. The equation should involve the equation I set up should involve the things that I have information about and the thing that I want information about. So what do I have information about? I have information about this side. I have a lot of information about that side. It's always 50. I also have information about theta. I at least know what theta is at a particular instant. And then what I want information about is x. I would love to know the rate of change of x because that's the speed of the bird. So I want an equation involving theta and 50 and x. And so I think about the trig functions that I know. Relative to theta, this would be called the opposite, and this would be called the adjacent. So I'm thinking of a trig function that involves opposite and adjacent. I'm thinking of tan. Tan theta is opposite over adjacent. And that is my equation. So from here on out, here's what's going to happen. I'm going to do the derivative of both sides. Then I'm going to plug in values that are valid at the instant in question. And then I'm going to be able to solve for what I want, which is the rate of change of x. All right. So here goes. Let's do the derivative of both sides. And I'm doing the derivative of both sides with respect to t, time. So here's how this goes. Here I have tan theta. The derivative of tangent is secant squared. But I'm not done because I'm doing the derivative with respect to time. So every time I do something like this, I have to multiply by the derivative of the inside. This is like the chain rule. The inside is just theta, and the derivative of theta is this. Remember, I'm doing the derivative with respect to t. When I say with respect to t, that just means t is like the variable that goes on the bottom for this. Whenever I do a derivative, it's going to be d whatever over dt. That's what it means to do derivatives with respect to t. And that equals what? Actually, let me be smart about this. Of course, I could do the quotient rule, but who wants to do that if I can avoid it? Let me rewrite this as 50x to the minus 1. So the derivative would be 50 times negative 1 x to the negative 2. But again, I have to do the chain rule. So I have to multiply by the derivative of the inside. The derivative, the inside would just be x, and so the derivative of x is dx over dt, once again, because I'm doing derivatives with respect to t. Okay. Now I'm going to plug in values that are valid at the instant in question. So I use this abbreviation at the instant in question. So at the instant in question, I should be able to find values for all of these things except one. And then that last one will be what I solve for. So what do I know here? I know that theta is pi over 4. So I can fill that in. Do I know d theta over dt? Well, d something over dt is just the rate of change of that. And I was told that that theta is decreasing at 1/10 radians per second. So I would say d theta over dt is 1/10, but it said it's decreasing at that rate. So actually I would say d theta over t is negative 1/10. All right. So I know that. What else do I know? Well, I don't know dx over dt, but that makes perfect sense because remember, dx over dt is exactly what we want. Like in the end, that's going to be our answer. That's the speed of the bird. So I'm not going to know that, but like I was saying, I need to know everything except one thing. So if this is the one thing that I don't know, I'm going to need to know x. And, well, if I read the question, it doesn't really tell me what x is. But that's okay. Sometimes we have like a little problem to figure out. We need to figure out what x is in the incident question. One way to do that is to just go back to your original equation. Another way to do that is to like draw the picture. At the instant in question, this is pi over 4. Pi over 4 is 45 degrees, so at the instant in question, this is just a 45, 45, 90 triangle, and so actually this is the same as this. So at the instant in question, x is 50. There's another way to figure that out. Like I was saying, you can go back to the original equation and plug in what you know. In the original equation, if I put in pi over 4 for theta, tan of pi over 4 is 1. So if I put in pi over 4 for theta here, I get 1 equals 50 over x, and then that would also tell me that x equals 50. So either way, if you just want to look at the triangle and say, well, this is a 45, 45, 90 triangle, so obviously this is the same as this, or you can go back to this equation. Either way. Okay, where does that put us? Well, we wrote down numerical values for all but one thing in this equation, so I'm going to put in those numerical values and then solve for the last thing that we didn't know. Okay. Right, so what's the secant squared of pi over 4? Maybe I'll go down here. Cosine of pi over 4, this is cosine of 45 degrees, that's 1 over root 2. You should know that. So then secant of pi over 4 is the reciprocal of cosine, so that would be root 2. And then so secant squared would just be 2. So that's me plugging in pi over 4 here. So this works out to 2. D theta over dt, we said, was negative 1/10. So then I've got negative 50 times, and then x was 50. And dx over dt is the one we didn't know. Okay, the rest is basically easy. I just have to crunch these numbers. So here I've got negative 1/5 equals, let me be careful here, because 50 to the negative 2 would be 1 over 50 squared. And then I can cancel a 50. So I get negative 1/5 equals negative 1/50th dx over dt. So then I guess I'm going to multiply by negative 50, and then this will just give me 10 equals dx over dt. Now, we should put units on our answer. The easy way to do this is, if you're talking about dx over dt, the units should be the units of x over the units of t. The units of x are, let's see, x was a distance, and in this problem, distances were measured in feet. So x is in feet, and t is time, and in this problem, time was measured in seconds. When we were given a rate, it was in rate like radians per second. So time is in seconds. So the bird is going 10 feet per second. I think that's a reasonable speed for a bird to go. I tried to use a reasonable number. Okay, so that's your related rates problem. The hard part is typically just setting up your first equation. And for that, it can all, I mean, not to scare you, but it can always be different. You just have to read the setup for the problem and come up with an equation that represents that. That can be the hard part. Not that the rest of it is so easy, but the rest of it is kind of always the same. All right, last one for this. Linear approximations and differentials. So we had a quiz question that was sort of similar to this, where you were asked to find an approximation of a particular number. So here's how this goes. I'm going to ask you to approximate something that is, like if it's a root, it will be something that's close to one that's really doable by hand. So let me explain. The square, or the fourth root of 16 would be doable by hand. The fourth root of 16 is just 2, right? Because 2 times 2 times 2 times 2 is 16. So that's the first thing to notice, is that the number that I want to do the fourth root of happens to be kind of close to another number that I could easily do the fourth root of. So that's the first thing to notice. But other than that, here's what I'm going to do. I'm going to define a function that is basically the function that we're trying to evaluate at whatever number. So what do I mean? I mean, I'm going to do the fourth root of x. So, you know, what we're trying to do here would be f of 16.8. And we're not really going to find f of 16.8, but we're going to find an approximation of f of 16.8. So these are the first steps. What I'm going to do and by the way, the instructions say use linear approximation or differentials. I always use this one. Well, I don't want to say always. I did a couple of examples with differentials, but I prefer to use this one if I'm given an option. So I'm going to find the linear approximation, or also known as the linearization, of f of x at a particular value of x. I'm going to choose the nice value of x, the value of x that I could easily do, 16. Linearization has this formula. It is, oh, now I have to, say we're doing the linearization at x equals a. Here's the formula. Oops. There we go. So we're doing the linearization at x equals 16. So for us, I need to find f of a, so that's f of 16. And this is why we noticed what we noticed, because f of 16 is just 2. It's important that we're able to do this one easily and find a nice round value like 2. So that's that. I'm also going to need to know f prime of 16. So f prime of x is what? Well, this root is really, it's like x to the 1/4 power, so the derivative is 1/4 x to the negative 3/4, because if I take 1/4 and subtract 1, I get negative 3/4, right? What I really want is f prime of 16, which would be 1/4 times 16 to the negative 3/4. I don't have a calculator, and I don't think I need one to do 16 to the negative 3/4 power. There's a couple of things going on here. First of all, I have a negative power. So that would be 1 over 16 to the 3/4. How do I do 16 to the 3/4? That's the same as the 4th root of 16 cubed. 4th root of 16 is 2. 2 cubed is 8. It's 1 over 32. Okay. So L of x is 2 plus 1 over 32 times x minus 16, because a was 16. All right. So what is our final answer? Once again, all we're trying to do is we're trying to approximate f of 16.8, the 4th root of 16.8. And f of 16.8 should be approximately L of 16.8. This L is an approximation for f. So instead of plugging 16.8 into f, I'm going to plug it into L. And L is easier to work with. If I'm putting 16.8 in, then this is just going to be 0.8, right? And to show you how much I really don't need a calculator, this is like, this is like 8/10, right? And so this would be like 8 over 320. 8 goes into 320 40 times. And I'm going to even give you a decimal without using a calculator. I know that 1/4 is 0.25, so 1/40th is just a tenth of that. So instead of being 0.25, it's going to be 0.025. So this is 2.025. That is my approximation for the 4th root of 16.8. And yeah, you shouldn't need a calculator for the one that I'm going to give you. I know at some points maybe I was barely getting by without a calculator. But you should be able to do this without a calculator. I'm going to give you one that you can do without a calculator. Probably slightly easier than this one, but still. Okay.